So up until now, we have been looking largely at an electromagnetic wave that is traveling in a medium which is unbounded, and in particular, the best case we have seen is when the medium alongside of being unbounded is also homogeneous, and so that means that there is no free charge in that medium, and therefore it acts like a perfect dielectric, making the wave propagation smooth and without any loss. So now that is the most idealistic case which you can assume, and such sort of cases are valid for long distance transmissions, for example satellites in space, where the distance can be effectively thought of as nearly infinity, and space being almost like vacuum can also act like a very good dielectric. So now we need to look at the more practical case where a wave is very likely to travel across media boundaries. Now, if you recall, in our discussion so far, we have discussed what happens when a wave is traveling in either a perfect dielectric or a dielectric with some conductive properties, or a wave which has extremely good conductive properties. But we've always been sort of playing safe by saying that the let us assume that the wave is just traveling in the medium without worrying about how it crossed into that boundary or how it crossed into the medium. So now slowly it is time for us to start looking at these things also. Let us say when a wave, let us say when you are making a call from your mobile phone, the wave is leaving your phone, it is going into the air, and then it is about to go out of your window, and then it hits the glass in your window, and then something happens to it and it goes out. And suppose just outside your house there's a metallic obstruction that is sitting, so that will again cause the wave to behave in a certain different manner. So now the baseline physics behind it is something that you already know. So the baseline physics that we already know from high school, that is when a wave travels from one medium to another medium, or rather tries to travel from one medium to another, things like reflection or refraction may happen. So we have to now delve deeper into this phenomena and try to understand that even though intuitive knowledge tells us that reflection or refraction may happen, what happens to the field components of these waves? We have also established some conditions regarding fields when they are at media boundaries. When we were discussing Maxwell's equations, we claimed that these are called as the boundary conditions. So with our knowledge of propagation of the electromagnetic wave, and also our knowledge of boundaries or the boundary conditions, equipped with these and also a few other things that we are going to discuss now, we will understand deeper into the physical phenomena of what happens when a wave tries to cross the boundary between two media. So when we were discussing about wave propagation so far, We have conveniently assumed that, let us say, if this is the Cartesian plane, let us say this is the x-axis, then in that case, this must be the y-axis and this is the z-axis. So this is, you will notice that this follows the right hand thumb rule of the cross product orthogonality perfectly. So let us say that we were assuming that let the E field exist along the x-axis, the H field exist along the y-axis, but the wave travels along the z-axis or something like that. We had discussed this to make our life easier, but in general, the wave can travel ideally in any direction. So if it travels in, let us say, this direction, then the electric and magnetic fields will look something of this kind. So the point being is that the orthogonality is still maintained no matter how difficult the mathematics becomes. So now for us to understand, or rather to take this new step of looking at wave propagation across the media boundaries, it is a better practice to now assume that the wave be traveling in any direction, not necessarily along the x, y or z. Why? Because let us reserve the definition of the Cartesian axis for the media boundaries. So let us say So let's also assume that the wave can travel in any oblique direction. Oblique means something which is not normal. So the wave is not traveling along any of the three axes. Okay, so oblique means not along any single axis. So the implicit understanding, as I said, that if the wave is traveling in this direction, then the E and H fields will also reorient them in some oblique fashion. So that is the implicit understanding. Now, without considering so much about where the fields are, but rather assuming that the fields are there and they are behaving in a proper way, let us go back and define some properties of the wave propagation. So let us say this is my x-axis, this is my y-axis, this is my z-axis. So let's call this origin as point O. Now let's make an assumption that the wave is traveling along any direction in 3D space. Let's suppose this is that direction. So since this direction is not along either x or y or z, let the unit vector along the direction of wave propagation be denoted as some n cap. What n cap is, we will see later. So now let us say that I am starting to measure the distance of the propagation from this origin point. So if the wave is traveling in this direction, I can define multiple points along this axis, which essentially corresponds to how far the wave has traveled from the origin. So by now, you will know that as per our definition, the spatial phase of the wave, that is the phase due to the distance it has traveled. That is nothing but, what is it? Turn back the pages and you will see it is nothing but beta times the distance traveled, where beta is the phase constant. So remember, there was this term omega t minus beta z. So where omega t is the time phase and beta z is the space phase. So most of the time we assume that the time phase is implicit. So in the case of when the wave was traveling along the z direction, the space phase was beta z. Now it will not be beta z, it will be beta into whatever is the distance traveled. So this is what we know. Now what may happen is that, or rather what will happen is that even though the wave is traveling in this direction, the individual field components will constitute some kind of a transverse phenomena which is perpendicular to the direction of propagation. So what we can define is that along any point or at any point on the wave, now whether suppose let us say the wave is traveling this way, so one field will behave like this, the other may behave something of this kind. So the point is, whatever field you are looking at, let us say this or this, it will correspond to some spatial phase which is determined by the distance. Let us say the origin is over here, this distance or this distance. So whatever point on the wave we look at, it will give me some value of the space phase. So to define this in a better way, we will define something called as a wave front or a space front, or sorry, a phase front. So if you recall your wave optics topic from your high school physics, you will remember that the physicist Christian Huygens had proposed that a plane that is perpendicular to the direction of propagation or perpendicular to the wave propagation direction, we can call it as a wave front or a phase front. So that plane may be very large in size, very small in size, that is immaterial, but let us define that plane. So this we call as either a wave front or a phase front, and this plane will be perpendicular to the direction of the propagation or the n vector. So let us say the wave is traveling, and on this, the point at which the phase front is meeting the wave, let's call this point as A. So we can also say that at any point on the phase front, or some component of the wave will also exist due to the individual fields. Let's call that as P. Now, Now, let us say that since P denotes any point on the wave, so let's define these quantities. A is a point on the direction of propagation, and P is a point on the wave, that is at any of these transverse components. So without worrying which point on the wave it is, we can just define some point P. So let us define the distance OP as some r, which is also called as the radial vector. So you can define it as a vector also. So now, if the direction of the wave propagation is not along any of the axes, but we know what is the angle it makes with each of these axes, then our work becomes easier. So let us say the direction of the wave propagation, or the n cap vector, is making an angle phi x with the x-axis, some angle phi y with the y-axis, and an angle phi z with the z-axis. Then how can we define this n vector? So this n vector is nothing but the projection of this vector on each of these axes. So then using this, I can now say this n cap is nothing but, so the projection of n cap on the x-axis is nothing but cos of phi x. So it will be cos phi x x cap plus cos phi y y cap plus cos phi z z cap. This is what is n cap. So this is how we define it, and each of these cos terms, that is the cos of phi x, phi y and phi z, these give a sense of the measure of the wave propagation or the projection of the wave propagation along either axis. These cos quantities are called as direction cosines. So now let us consider this point P, which is a point on the wave, and let us call this as some x comma y comma z. So what is this r vector with respect to the origin? So this r, I can define it, is nothing but x cap plus y cap plus z cap. Now, if I want to take a projection of this r vector along the direction of propagation, what do I need to do? So the projection of this r vector along the direction of propagation is nothing but the dot product of the r and the n cap. So I can say the projection of OP, or that is the r vector, along the direction of wave propagation that is nothing but R dot n cap. So we already know what that is. R is this and n is this. So we just take a dot product. It will be the multiplication of the individual terms and adding them up. That is nothing but x cos phi x plus y cos phi y plus z cos phi z. So, as you know, this is a scalar. Now, if I multiply this r vector or the dot product of the r vector and the n vector, you will notice that it is multiplying this r vector along with a vector of unit magnitude. So this is nothing but the mod of the r vector itself, because the mod of n cap is 1. So multiplying any non-zero or non-unit vector with a unit vector will always give me the mod of that unit vector if it is a dot product. So now if I know this product, I can calculate the space phase or the spatial phase corresponding to this point. So that is nothing but, as you know, beta times the distance. So distance is the mod of the r vector. So that is nothing but, let's call this as the spatial phase as some phi. Do not confuse it with the direction cosine. That is beta times mod r. So that becomes equal to what? So it's nothing but a scalar product of these two. That is beta x cos phi x plus beta y cos phi y plus beta z cos phi z. But we already defined the r in one way, that is x cap plus y cap plus z cap. So I can sort of rewrite this particular sum of product expression using two vectors, which is like this. A dot product of x with beta cos phi x plus beta cos phi y component plus beta cos phi z cap. So essentially what is happening, I can take beta as common. So this is nothing but the r vector times beta times what? So if I take beta common, it is cos phi x cap plus cos phi y cap plus cos phi z cap, and that is nothing but n cap. So it is beta n cap. This is the space phase for this point. So I can write this as r dot k, where k vector is nothing but beta times the n vector. This is what I can write. So since the space phase is now given as a dot product of the the radial vector and the k vector, which corresponds to the projection. So earlier we were writing, let us say if I have an electric field E, I was writing it in this form: E0 along some direction, e raised to minus j beta z component. This is the old or earlier. What I can do now we know that it is not traveling in the z direction. So the new representation, I can actually absorb the unit vector n along with E0 and represent this as a vector term. I can say this is nothing but some E0 bar where the unit vector along the direction of propagation is, oh sorry, this was x actually, something of this kind. This is not z. Z is the direction of propagation. So this x I can actually absorb over here into the E0 and call that as a vector. And the space phase I can write as e raised to minus j. Now the space phase is this. R dot k, without worrying about what the exact axis is. Now whatever are the axis functions and their projection functions, they are all absorbed over here. So this is the new representation. So I don't have to worry about whether E is now along the x direction. It can be some direction which is orthogonal to this. So orthogonal to the direction of propagation, that is n. So now let us say if the wave that we are considering is having some electric field component which is represented in this form. The obvious question is now, what is the magnetic field? What is the magnetic field H? So we can use Faraday's law and calculate it. So let's write this again. This E vector is nothing but E0 vector times e raised to minus j r dot k vector. So in general, again, it will have some ex, ey and ez component that will always be there. So if I want to find the H, the magnetic field vector, by now this would not look any new to you. Using Faraday's law, I can say that this is going to be my H vector. So this is nothing but minus 1 by j omega mu, the curl of the E field. So let's write that. So here we will have the x derivative, the y derivative and the z derivative with the ex, ey and ez components. So we can say that just like how we represented the time differential as similar to multiplying by j omega, we can also define that differentiating with respect to x for this E field will be very similar to multiplying with minus j times beta cos phi x. You can do that. So when you take the derivative of this constant term will come out because the phi x is a constant. So therefore, this is what this j times this beta cos x will get multiplied. Because r is a function of x that will be differentiated, and what will be the constant on the exponent will be minus j times beta cos x. So likewise, I can define these also. Multiplying because it's an exponential term. So the derivative of an exponential is essentially the same thing. So that's why it reduces to multiplication, similar in the time domain. Now this beta cos x, I can write it as some kx. This I can write as some ky, and this is z. So this and this will now become minus 1 by j omega mu x cap, y cap, z cap. So now we will replace these derivatives with our new quantities. And here we will have x, ey, z. So without doing much hassle, you can see that this becomes minus 1 by j omega mu. Now I take the minus j common, this will be into minus j times, this is nothing but a cross product of the k vector with the e vector. So k vector is nothing but the beta times the direction cosines. So this is nothing but k cross e, this same k. So this minus and minus will cancel, the j and j will cancel, and what I will get is 1 by omega mu k cross e. So what do we see from here? What do we see from here? We see that the magnetic field H is a cross product of E with some other vector, and that essentially proves that the two are perpendicular. So it's perpendicular to both of these, in fact, where E is the electric field and K indicates the direction of propagation. So no matter what our frame of reference is, whether the wave is flowing along some axis or along any particular or any non-trivial direction, we can still prove that, or we have still proved that the H is perpendicular to the direction of propagation as well as the electric field. So therefore, if you recall, we had said that while solving for the wave equation, we had said that we'll go for the simplest solution and assume that it can be extrapolated. So this is what I meant. So let's go ahead. So what we saw is the H vector is nothing but 1 by omega mu k cross E. So what is k? We had defined k using beta in this format. Let's put that. So if I can take this beta outside and say that this is beta by omega mu, and this will be n cross. I can write this E using this way which we had defined earlier, that is E0 times. So now this will be the cross product and the exponential term will come outside. So now let's suppose the wave is traveling in a lossless medium or a perfect dielectric. Then for that the beta is nothing but omega under root mu epsilon that we have defined already. So beta by omega mu. So beta by omega mu will be what? Omega so this will be nothing but epsilon by mu. So I can substitute this and I can say this is nothing but epsilon by mu times this quantity so what is this? What is this? This is nothing but the reciprocal of the intrinsic impedance. So I can say it's 1 by eta so now what I'm doing is I am taking a cross product of the electric field vector along and the direction of propagation. So that we already know will give me the direction of H. But we have also seen from our discussion on electromagnetic waves that the mod of the magnetic field component is nothing but the mod of E0 by eta. So this will essentially become some H0 times e raised to minus this. So the direction of propagation of E and H fields are the same, except that the way they exist are along orthogonal planes. So this is what we have proved. So let's go ahead. So if you recall, we had defined that if the wave is traveling along this direction and we had taken the wavefront or the phase front as a plane perpendicular to the direction of propagation. Let's rewrite this. Now let us assume that along with the wave, even this phase front is moving. So the velocity with which the phase front is moving, suppose we had taken these 2 points P. Now obviously the P will move with time. So let us say that even this phase front, this plane is also moving along with P. So whatever is the velocity with which this phase front is moving is called as the phase velocity Vp. So this is what we call as phase velocity. That is Vp. So now often it so happens that if you are working with media where the wave is propagating in any particular direction, it may sometimes be little difficult to catch that in practice. So what we do is, we, rather than trying to hunt for where the wave is actually, we try to see what is the projection of the phase velocity on the three axes. So what you can prove is that if the phase velocity is some Vp, then we can project that the velocity that will be actually seen on the three axes, that is Vpx, Vpy and Vpz, will be nothing but the phase velocity Vp divided by cos phi x. So this will be Vp by cos phi y, and this will be Vp by cos phi z. Now I shall not tell you how this is coming. I shall not prove this. But one hint I will give you. It is to do with the velocity of the phase part, which is perpendicular to the direction of propagation. Now with this, I leave the proofs of these three to you as an exercise. So do try this out. Now what we are seeing is, in general, the phase velocity components on all the three axes are given as this. So let me just write this. So in general, when the wave is oblique in some fashion, phi x, phi y and phi z are neither 0 nor pi by 2 nor pi, something of that kind. So in that case, it is interesting to note that the mod of cos phi x, mod of cos phi y, mod of cos phi z, they are all less than 1 in most cases. So what we will see is that the velocity that we are measuring on the three axes will actually be more than the phase velocity. So let us say if light is traveling, then the velocities that we will measure will probably be more than the velocity of light. So what this indicates? So can we say that in general there is a possibility to send waves faster than light? Well, think about it. Obviously it is not, because we are talking of the components of the velocity, not the actual velocity. So after defining phase velocity, we define the actual velocity of the wave. That is what we call as the group velocity. So generally it is the velocity of the wave, not of the phase front. So what we can say is that if this is the actual velocity that we measure, this is nothing but the beta by omega. This is the way we measure it. So if the wave has multiple frequencies, then the group velocity is what you should look for, or the velocity of all possible phases or frequencies So that is also called as Vg, or the group velocity, or the velocity with which the energy is flowing. So this is what is more important. So if Vg is in this direction, so now since the velocity is in this direction, we can define the three components Vgx, Vgy and Vgz as the group velocity times cos phi x, this as cos phi y times Vg, and this is Vg times cos phi z. So these are the three components. So if you now look at the relationship between the phase velocity and the group velocity, you can see that because of in one place because of the cos terms coming in the numerator and denominator. So if we take a multiplication of oops, I'm sorry, this is not omega by v. This is the velocity of the energy flow. So it may or may not be equal to beta by omega. So if I define the wave velocity v, that is nothing but omega, or rather beta by omega, this will be essentially nothing but the product of the group velocity and the phase velocity. So group velocity in general can be less than or equal to the wave velocity. The phase velocity can be more than or equal to the wave velocity. So this should be the bit velocity square, which is nothing but the product of the group and phase velocities. So the actual wave velocity will be the geometric mean of the group and phase velocities. So in general, I can have Vg less than or equal to V and Vp more than or equal to V. This is what it is. So we shall continue from this point onwards in the next class.